Hi, today I'm going to present you the efficient unsupervised shortcut learning detection and mitigation in transformers paper. I'm Lucas Kuhn, I'm one of the authors of this paper, and I'm going to walk you quickly through our poster to explain the method, and then I'll walk you through the code so you can actually run it for yourself. So what did we actually do? We are trying to mitigate and detect shortcuts learned in vision models. So what are shortcuts? Shortcuts are spurious features that are actually irrelevant to the task which made it into the dataset. Let me give you a quick example. We have the ICCV dataset in front of us here in the pipeline, which is a dataset of skin cancer detection, and the classes are benign and malignant. But for some of the benign data samples, there are actually colored patches, which you can see here, or you can see in the big training image, this red colored patch, which got put onto the patients for color calibration of the camera. This is only on benign patients, so some vision models, or a lot of them, actually pick this up as a spurious feature of classifying images as benign. So if we put a color patch on a malignant sample, we can actually see that it gets wrongly classified as benign because it got picked up as a spurious feature. We are trying to eliminate that with this unsupervised pipeline. So this is without knowledge of what the actual shortcut is or where it is in the image or in which images it is actually present. So we wanted to make it completely unsupervised to run as a full pipeline. So let me walk you through this main image here. We have a training image, which, as I said, is from the ICCV dataset, and we are running it through the vision transformer with the n blocks. At the last block, we actually get the activations, which is meaning all the activations of the different tokens in the embedding dimension. This 768 dimensional representation, which we get from our vision transformer, from the normal vision transformer B16, we can actually then cluster. And when we cluster it, you can see it here on the image, we actually get a nice clustering between two different separate clusters, which we then select prototypical samples from. Prototypical samples meaning we pick 10 or 20 different samples out of the center of each cluster. And what we can see from these clusters is that when we pick prototypical samples, that we actually get shortcut reliant samples in one cluster and non-shortcut reliant other samples in the other cluster. We then select from these different clusters prototypical patches, which is done by comparing each token here to all the other tokens in the other cluster and getting the mean from that. So we can actually get a distance between a token from here and all the other tokens in the other cluster. And this obviously results in us finding those colored patches because those are not present in cluster 1 and they are completely different to what is in all the other images. So we can see here in cluster 2 that we selected all those colorful patches, and in cluster 1 we actually selected some samples of skin or dark spots in the skin of the patients. And with that information, without knowing if something is a shortcut or not at this point of time, we give it to Lava and Llama for captioning and for summarizing what is in all those different prototypical patches. So we take each patch and we give it to Lava. We say, please caption this patch for us, what is in there. And then all those different captions we give to a large language model, and we actually get a nice cluster description. For example, for cluster 2, we get the description circular shapes and colors, particularly yellow and orange. And for cluster 1, we get hairs or small other dark features on skin. We could then either give this to a domain expert, as we have it here in the pipeline, and he can say, because some spurious features are obviously subjective to the task at hand, and he can actually say cluster 2 potentially describes a shortcut, because I wouldn't expect circular shapes and colors on those images to be of any meaning to benign or malignant classification of skin cancer. Or we can take a metric that we developed that you can find in the paper, which does that automatically, which is a mix of homogeneity and differences between those two clusters to actually select a cluster as a shortcut. So what do we do with this information? We now actually have prototypical patches for a shortcut cluster, and we have prototypical patches for a normal cluster. And when we run a test image, we can, because we are using a vision transformer, we can actually eliminate tokens from this test image before running it through the full transformer architecture. So that is what we do. We eliminate tokens, for example, from this test image by using k-nearest neighbors between all those different prototypical patches from cluster 2 and the prototypical patches from cluster 1. And we can see if one of those tokens here actually isn't closer to the shortcut cluster. If it is, then we ablate this. So we remove the token from the sequence. If it is not, we obviously don't remove it because it's part of a real image and we want to use it. So we actually remove the shortcut from the input data, and then we run it through the vision transformer. And this actually gives us, for this example, because we put this patch here afterwards, so we actually get a malignant classification and not a false benign classification based on the spurious feature. So this method of removing from test images, removing tokens from test images, can then obviously get used for last layer retraining or just train twice, or different other methods afterwards, because we can remove those patches from the data set and then we can retrain the last layer, which is what we did. You can see all the results on the right side, and we actually see a big improvement already from just removing them from the dataset, but we actually see a larger improvement if we use last layer retraining on top of that, which is also part of our method. Then we remove the tokens from the dataset, and then we do last layer retraining with this new dataset, and those are the ASM results you can see here on the right. And we actually ablated this as well, and we have a without retraining results, which are the ones below, and you can actually see that we get state-of-the-art worst group accuracy and average group accuracy with that pipeline, and it's completely unsupervised. You can use a domain expert, you don't have to, but it works for different data sets and it works for different patches. And now I will quickly walk you through the code. Let me now walk you through the Jupyter Notebook, which you can find in the GitHub repository. I ran all the code blocks beforehand, so you can spare a little bit of time. Runtime is actually not that high, even on a MacBook M3 that we are running this on right now, but I didn't want to load up the video by just waiting here for results to finish. So those are just the usual imports. We're actually using the ICCV dataset as well here. Don't be confused that I split it into without patches and with patches. You obviously don't need this information, as I told you before. It's completely unsupervised. This is just to actually report results on patches and non-patches for the paper. And I actually run the sample now so we can see how well it works during running. You obviously don't need this information in a real life sample. So this is just loading of the validation test data set. This is loading of the model, which we trained beforehand on the ICCV dataset as it comes, so with spurious features in there for the benign samples. And then we just do test dataset inference, and we can actually see that the worst group is the malignant group with patches. So we added patches onto some malignant samples, and this is what you can see here, because there wasn't any natural spurious patches on those malignant samples, so we added them via Photoshop on there. And you can actually see that this is our worst group, which we obviously want to get much better than 0.56. And we actually have another really bad group, which is the 0.73 group, which is actually malignant samples as well, but without patch. And the benign with patch is 100%. So this is obviously the spurious feature at play, which makes it pretty easy for the classifier to classify them as benign. So the next couple blocks of code are for the extraction. As I told you, we're extracting the last layer activations, and we're meaning over that. So this is all that is going on here. And then we're just putting them into those different arrays so we can use them later. And for on those activations, we then perform PCA first with 50 components, and then we are doing k-means clustering in this space. And as I told you on the poster, this k-means clustering enables us to find different clusters. For this example, we have 2 clusters. You can actually find them by the elbow method or other methods if you want to. We actually tried that as well, and it works completely fine. For this, I pre-selected 2 clusters. And we are doing k-means clustering. We get a result of 0.77, which is actually fine. We don't expect perfect clustering. We can't expect perfect clustering because it's spurious features mixed in with others as well. There are some data sets which are a little bit higher and some which are a little bit lower. They all work fine because that's not what we rely on for the selection of the shortcut. Then we have a prior score and class homogeneity evaluation of the clusters, which is our unsupervised method of selecting which cluster is a shortcut. You can read more about that in the paper, but we actually see that cluster 1, which is the cluster, which is actually the cluster with the shortcut, has a 0.85 in this metric, so it is selected as the cluster with the higher score. As you can see, you can read more about that in the paper of how we actually come up with this unsupervised metric and how it works. This could also be the domain expert that I referred to earlier in the poster, which can decide later on the descriptions of the different patches, which cluster is which. But we did it beforehand. We did it completely unsupervised in this pipeline. All the results that we reported are actually unsupervised selection results, and we basically have a 100% hit rate of the right shortcut cluster with this metric. So then we are running the prototypical sample selection here. You can actually see cluster 1 has a lot of those benign patches in there. Cluster 0 as well for some images. Which is why we have the 0.77 accuracy that we saw earlier, which we got from the ground truth spurious feature results, which you don't need again. So you can see some of those spurious features actually also made it into the other cluster. This does matter. We will also not rely on this for selection of the patches, because we will then, as I told you, calculate the Euclidean distance between those tokens and the other cluster. We also have a nice visualization of that. So this is what we are doing in here. And you can now see the distance heat maps for each of these previously selected samples up here. You can see it here. And you can see that the heat map actually shows those benign patches really well on those cluster 1 samples here. And then for cluster 0, we get all kinds of different heat maps, because the distance from here to here for benign patches that actually made it into there is not that high, because we have a lot of benign patches, a lot of colored patches in the benign samples in cluster 1. So this is actually how we select the right patches from those images, the right tokens that we then want to use. So then we actually extract all those different tokens from here. So we'll select the highest heat map tokens from all those different samples here, and then we run them through Lava and Llama. So an expert could classify the clusters as shortcut or non-shortcut with this description that we then get. I will skip that part because we don't need to run an LLM now. We use the unsupervised method, the unsupervised metric that we devised earlier to already select cluster 1. But just so you know, you can put your replicate API key here, and then you can run it, and you get descriptions of those clusters that you can also read about in the paper. So what we are then doing is actually outputting all those different clusters here just for visualization, and we can then evaluate what patches we actually selected from those different, what tokens we actually selected from those different samples. Those are actually also the ones that we are then sending to the LLM. And you can see for this year, it's actually a lot of the shortcut, a lot of the spurious feature colored patches. We actually have one here as well, which doesn't matter too much because the LLM will, when it summarizes, basically ignore this because it's just one sample. So this could happen that this actually has the highest distance, but it's not too impactful on the whole pipeline because, as you can see on the bottom, we clearly have selected the shortcut here. So then we extract the 100 most distant keys for each cluster and the 100 lowest keys for each cluster. So we can actually we actually want the 100 lowest from the first one and we want the 100 highest from the second one, because lowest would mean they are similar in both clusters, and highest would mean that they have the most distance between each cluster. So if we have the most distance here, we can see the shortcut. If we have the lowest here, obviously it would be shared points as, for example, the skin points, the darker skin parts in those images. So what we are then doing is we are using the KNN classifier. We are training it with the 100 lowest keys from cluster 0 and the top 100 keys, the highest distance keys from cluster 1, as we selected previously. And we are doing KNN with 5 neighbors. You can adjust the neighbors if you want. Doesn't have too much of an impact on the final results anyway. What we are then doing is we are basically dissecting our vision transformer so we can remove the tokens, which is what we are doing here in this helper code. So we are removing the tokens based on the KNN classification. If the token is a shortcut, we remove it from the tokens in the input, and if it isn't, we actually obviously let it be in there for classification. If we now perform this method on our test dataset, you can actually see that we already increased the accuracy from 56% to 61% and from 73% to 74% without actually impacting the other metrics. So we are not actually getting worse results from the benign with patch, which is pretty nice because it's still classified as benign. Even though we remove the colored patch from there. What we can then do is we are doing last layer retraining, or called DFR, deep feature reweighting, with this new data set. So we actually come up with a new data set based on, or we create a new data set with the now ablated tokens. So some input images have missing tokens now because we removed them. Because we think they are a shortcut, and we actually are building a new data set out of that. This is the custom data set that we have here. And then we're actually just retraining the last layer. So we're actually setting all the weights to false except for the last layer that we have here. And then we are retraining it for 5 epochs. You can train for longer epochs. You can do a little bit of hyperparameter search here if you want to. Doesn't have too much of an impact on the final results. It basically works out of the box with the hyperparameters that you have in this Jupyter notebook here. Then we're actually running 5 epochs of training on this new data set with the ablated tokens, and we are running it. And then we are doing inference on the test data set again, and we can see that the results now improved even more than before with the deep feature reweighting. We have a little bit less of performance in one cluster, which is to be expected with deep feature reweighting, but in total we get a higher average group accuracy and we get a higher worst group accuracy, which is the result that we are reporting for all the different seeds and all the different data sets in the paper. And with that, we are done with the Jupyter Notebook. I hope you enjoyed this small presentation of our paper, and I would love to see you at our poster session.